everybody. So I want to start off this next segment with an explanation of this particular problem, example 3, that we did in class and that you were supposed to try last night. But I want to explain it to you anyway so that this way you have a working explanation of it. So when I look at this problem, the first thing I notice different from the first two is that it has a shape associated with it. And for me, that shape, we have a pool, and it has a height and a diameter. And so really, and I'm not a great artist at this, what we have is we have a pool that looks like this. And this pool is a cylinder. And so I know that my cylinder, the volume of a cylinder, is pi r squared times the height. Now this problem is also challenging because there's really two things going on. We're filling up the pool with a hose, so that's an issue. But we also have, well, how much do we need to put into this pool? And so I need to find the volume of the pool. And I really want to find the volume in milliliters because my rate of filling up the pool is also in milliliters. From there, I can find out how many minutes, hours, days. So I start with the volume. So when I start with the volume, I want a volume in milliliters. And a milliliter volume is centimeters, excuse me, let me switch that up, centimeters cubed. So I have a pool with a height of 4 feet and a diameter going across of 72 inches. So if my diameter is 72 inches, my equation has a radius in it. I need to change that to 36 inches. And I can change that to centimeters. And again, the conversion factor, 2.54 centimeters for every 1 inch. So that'll give me my answer in centimeters. So 36 times, calculator isn't working, 36 times 2.54, and I get 91.44 centimeters. Then I also have the height in 4 feet. And so this I can also change to centimeters. I'm going to do it in 2 steps. And so when I go ahead and I do it in 2 steps, then I would have 12 inches times 12 inches over 1 foot. And then when I do this again, I would have my 2.54 centimeters over 1 inch. So if I plug that in, 4 times 12 times 2.54, and that's 121.92 centimeters. So now I can take these two numbers, I can plug them into my volume, and I can get my volume in centimeters cubed. So if we do that, we have pi times r squared, 91.4 centimeters, and we're going to square that, times the height, 121.92. And then we could calculate overall what the volume would be. So if I do that on my calculator, then I get that the total volume is going to be 3,199,759 centimeters cubed. So now I have the total volume, and that centimeters cubed, since it's the same as milliliters, that's going to also be milliliters. So now I need to change that into time. Well, if I have this volume, 3,199,759, and this is in centimeters cubed or milliliters, and I know that for every 1 minute, I'm filling at 500 centimeters cubed. I can then change that minutes to hours times 1 hour for every 60 minutes, and to days, 1 day for every 24 hours. So when I go ahead and do this, times, and I divide it by 500, and then I divide it by 60, and then I divide it by 24, it would take approximately 4.4 days to fill up this pool. So this is the worked out example 3 that we did in class, but here it is again. Now you can watch it on video, and you can pause the video and you can go back and forth and you can look at how I did the work. If you had trouble understanding it, if I went too fast, if the writing doesn't make sense, now you can go back and you can look at this again and make more sense of it. Okay, so let's move on to the next part of the chapter, and that is precision and accuracy. So you should know these key terms and have them memorized and understand what they mean. You might have an idea of what you think they mean. Accuracy means how correct the answer is, how close the answer is to the accepted value. So the idea is how close is the answer to the accepted value, and it could be very close or it could be not so close, accurate or inaccurate. And then we have precision, and precision is where you are reproducible. This comes from multiple trials. So let's look at the dartboards above here. On the left we have good accuracy, good precision. So ask yourself, why is that accurate? And why is it precise? And then in the second situation, we have poor accuracy, good precision. Again, does it fit our definition? Is it not accurate? Is it inaccurate? But is the precision good? And then you have the third situation, that's me shooting darts, and that is where you have poor accuracy, poor precision. So what about these different setups gives us accuracy versus precision? That's something that you need to think about. In the lab, we usually do multiple trials because we want to see if our results are reproducible. And we also want to try and get close to the accepted value. When we look at accuracy, we explore something called percent error. And percent error is equal to the error over the accepted value times 100. So how do I find the error? Well, the error, I take your value, your measured value, and I subtract it from the accepted value. And from that, I get the percent error. We're going to do some practice with that when we go and do labs, but you have to know that definition, what percent error is. With precision, although we won't do this year, do it next year if you take IB chemistry, with precision we do something called standard deviation. Standard deviation tells us how close all of the data is to each data point. Now, something that we're going to explore a lot is significant figures. And when we look at significant figures, we're really looking at how accurate we can get, how close we can get to the accepted value. And that depends on how many figures are in our measurement. People always complain about significant figures because a lot of times they don't really understand why we're doing it. Why are we trying to use these things called significant figures? And what are they? Well, let's look at a couple of measurements here and try and work out that definition of what significant figures are. So here I have a ruler, and I'm measuring this arrow down here. And I want to see how long it is. So go ahead, pause this, take a minute, look at it, measure how long that arrow is. And then also do the same thing for this sample right over here. Take a minute, measure it out. Now, when I measure out this arrow over here, I get 6.4 centimeters. When I measure out the water in this meniscus over here, I get 1.53. Let's say these are milliliters, so milliliters. Did you get the same answer as me? Maybe some of you got, for example, 6.5 centimeters. Who's correct here? Am I correct or are you correct? Well, what I'm going to tell you is that you're both, or we're both correct. Because what we have here, we have a certain value. And then we have an uncertain value. Together, the certain value and the uncertain value, when we look at both of them together, they make up the significant figures. That's how I define the significant figures. The significant figures are all the certain values plus, let me just rewrite values here, all the certain values plus one uncertain value. Let's say that another kid comes along and he decides that he's going to measure this ruler and he's going to have 6.53218 centimeters. Why is that answer nonsense? What's wrong with it? Well, this is something that we can discuss tomorrow in class. I want you to think about this question. Why can the student who picked up that answer in purple there not say for sure that he has 6.53218 centimeters? Why are 6.4 and 6.5 what we can say for certain and uncertain, but why we can say those are significant figures? Well, we're going to go through that. Let's look at this answer over here, 1.53 milliliters. What if I were to then go ahead and say, well, no, when I got this, I got 1.54 milliliters. Who's correct here? Who's incorrect? Again, we can't tell. Because we know, significantly speaking, that we have two certain values here. We know, for example, that the first number has to be a 1. And we also know for certain that the next value has to be a 5. What we don't know is, well, what comes after the 5? It's uncertain. We know that it's not 5.0, but we also know that it's not, 1.60. We know it's between there. And so we guess. We have one uncertain place. And whenever we're taking measurements, we'll always have one uncertain place. Now, we'll do some work with significant figures, but I want to introduce to you, and I wanted to introduce to you what significant figures actually are. It comes from measuring something. When you have a significant figure, by definition, it's all the certain values plus one of the uncertain values in the measurement. Now, when we measure stuff, we're going to be using two types of equipment. We're going to be using digital equipment and analog equipment. And when we use digital equipment, which is pretty much what we use most of the time when we do temperature, when we do mass, we use digital equipment. When we measure volumes, we generally use analog equipment, glassware, graduated cylinders, flasks, burettes, pipettes. You'll see all this equipment as we go through the year. But when we have digital equipment, we're looking at the smallest division on the equipment being plus or minus that division. For example, if I have a temperature that is 24.8, as I see here, okay, 24.8, the smallest division is the tenths place. I'm going to highlight that right here. That means that my value could be plus or minus one of those smallest divisions. In this case, it's the tenths place. It's 0.1. It could either be 24.7 or 24.9. It could be between those. When I report the value, I do 24.8 plus or minus 0.1. A lot of you are going to take the IB Sciences next year. You're going to enroll in that. This is going to be big. Any of the IB Sciences, they want to see that you understand uncertainty. No measurement that you take is certain. There's some variation to it. When we look at a piece of machinery, they call this uncertainty tolerance. What's the tolerance of the machinery? Now, analog's a little bit different. Analog, we have to divide the smallest division by half. So when I look at my clock down here, my smallest division is in seconds. The second hand, which I'll highlight, the second hand is between 20 and 21 seconds. I don't know exactly what it is. In this case, I say, well, it's 20.6 seconds. That's what I'm calling it right now. The smallest division is a tenth. So that's 0.1. So I'm going to divide this by a half. And so I'm going to have plus or minus half of that division, half of a second. So if my smallest division in this case is 1 second, then my smallest possible error could be a half, plus or minus 1/2. So it could be 21.1, it could be 20.1. We don't know, we're uncertain. Let's go back to that example that we had above, up here. What's the smallest division? Smallest division up here is 0.1. So that means that my measurement that I took, my 1.53 that I originally said, is plus or minus half of 0.1, 0.05. That means that my answer here technically could be anywhere from 1.48 all the way to 1.58. I don't know. In this case, I'm pretty sure that it's 1 point higher than 1.5. We can see that with our eyes. But technically, the error could range from half of the smallest increment. Again, with the clock, we have 1 second increments, so half of that smallest increment is a half. Now don't forget, with the analog equipment, we're going to be able to estimate this last digit. Even though it's an estimate, it's still considered significant. Let's try it with a piece of machinery here. So with this piece of machinery here, I have a triple beam balance. The first one is 200, that's certain. That's the hundredths. Then I have the next place, which is 50 and 60, tens. So I have 250, and then I have the next one, which is 6, 256. But I can see my smallest divisions here, which I'm highlighting right now. My smallest divisions are tenths. So I know that it's 56, 56.1, but I don't know exactly where that last one is. 56.1 something, I have to guess. This one here, which we'll guess in yellow, this is my guessed value here. It's my estimated value. 256.15. Now, the smallest value for this that's known is 0.1. 0.1 is the smallest increment or division. I half that, so my uncertainty is plus or minus 0.05. So what does this mean? This means that technically my answer could be 256.10 all the way to 256.20, somewhere between there. So what I'd like you to do is try that out for this one here. Tell me what you think the answer should be, plus or minus. In this case, I gave it to you. Here's another one, measuring with a beam bounds. Go ahead, see if you get this answer here or not, the one that I'm going to highlight. Is this correct? Give it a try. Pause the video. Here's one with a meniscus. See if you can get this same measurement they got. I'm going to stop the video here. When we come back, next time we'll talk about significant figures. And that'll be our last and final installment in this particular set. That's for our Unit 1. It'll be complete at that point. Thanks so much.